Okay, now we've just finished taking an exhaustive but useful look at several different circuits and seeing what happens to the potential differences, the voltages, in a complex circuit, and what happens to the currents, the charges moving through the circuit. And we came up with some interesting relationships, that they seem to have. These relationships are summed up in the following idea. They're called Kirchhoffs Rules. Now, hopefully I've spelled that correctly. I have a history of misspelling Kirchhoff. I think it's got 2 H's, but I could be wrong. Anyway, I do know that it's pronounced like this, like Kirk and then Ov. At least that's how I've always learned it. So please, if I'm butchering the name, then give me a little bit of latitude. I think he was German? I can't remember, and I'm not particularly good at German. I've always heard it as Kirchhoff. That's how I'll be referring to it in class. And whenever I've talked with other people who are in the know on it, when I say Kirchhoff, they know exactly what I'm talking about. Now, Kirchhoff was basically someone who did what we just did in the last 2 videos. He took some of the equipment, put it together, and started looking for relationships that happened in these circuits. And he noticed the things that we noticed. Now, it was a lot harder for him because he doesn't have state-of-the-art equipment like snap circuits and living in a world where we can go and buy batteries quickly and easily. That being said, he did come up with these relationships and he got them put together. They're known as 2 of Kirchhoff's rules. Now, they've got a couple of different names. They're sometimes known as Kirchhoff's voltage rule and Kirchhoff's current rule. I don't like either of those. You've heard me use the names already, and I'm going to reinforce those. I heavily recommend that you keep track of them like this. The first one that we looked at was called loop rule. I will call this Kirchhoff's loop rule in class whenever we're talking about it, but I'll usually simplify it to just loop rule. You don't need to know the name of the dead person. Loop is the important part that you want to remember. This is also known as the voltage rule. I do not recommend that at all. I'm not even going to write it down. Remember that this is loop rule. This one, more than the other one, is important that you do keep track of that loop. All right, what it does is it relates potential differences, voltages, if you will, in a circuit, specifically a closed loop of the circuit. I cannot emphasize that enough. Loop. The most common mistake people make is they forget the loop part of this. I know you're probably tired of me saying it, but I can guarantee you there's a reason I keep repeating it, because I've watched many students forget it, misapply it, and completely miss what they need to get in order to predict what will happen in real life. Do not forget it is the loop rule. All right, the other one that we just finished taking a look at, my red is a little sad face. Let's see. Let's see if this one's any better. Probably not. Not very red. Junction rule. This one's sometimes called the current rule. I still like to call it junction rule myself, but relates currents in a circuit. All right. Now that we've got that, that's kind of a rundown of what these things are. Let's go through and let's talk about them. In particular, I want to start off by looking at Kirchhoff's loop rule because it's the one that, honestly, I like a little bit more. It's a little bit trickier to apply, but it's very, very powerful. All right. So let's talk about loop rule. Kirchhoff's loop rule. Now, we've mentioned this before, but I'm going to go ahead and write it out so that you see it. The sum of potential differences. Normally, I'd be doing this part of the text in red, but my red markers are not my favorite. The sum of potential differences around a closed loop. Closed loop. I know you're probably tired of hearing me say it, but if it keeps you from making the mistakes, it's all worth it. In a circuit comes up or adds up to 0. I'm going to put a little note in here. My little notes I usually do in green. In case you wondered why I said this should be in red, I have a color code that I normally use in class. Titles and things in black, kind of their definition and things about them in red, equations in blue, and my commentary in green. So, for our purposes, batteries add potentials. Components, like especially resistors, remove. Or what you could say is batteries add potentials, resistors lower potentials. So your potential difference across a battery for our purposes is going to be positive, and the potential difference between or across a resistor is going to be negative. All right. In mathematical terms, it looks like this. The sum of, delta V, the sum of potential differences, or voltages, around a closed loop is equal to 0. All right. Now, we talked a little bit about this before. I mentioned it some, and I told you the best way to think of a potential difference is a lot like a height. It is related to not gravitational, but it's related to potential energy, but it is not itself energy. Just like gravitational potential energy, the energy is when we have the mass, the gravitational acceleration, or the gravitational field strength, if you'd prefer, and the height, mgh, gives us our gravitational potential energy. If we don't know the mass, we do not have the energy. We don't know how much energy there is. But if I say something is 10 meters in the air, or 100 meters in the air, then we know that they have a relative difference. The way I usually try and describe a loop rule is the following. Okay. This is a ski lift. I like to think of batteries as a ski lift, and that the circuit is like skiing. So, let's explore the idea of the ski lift first. What's the point of a ski lift? Well, normally what you do is when you're on vacation, you would hop on one of these, it would take you up to the top of a tall hill, and that gives you a lot of gravitational potential energy. Now, where did that come from? It came from the ski lift lifting you up. And now you're way up here, ready to do some skiing. And what you do is you then ski down the hill, and as you go down the hill, that gravitational potential energy gets turned into kinetic energy. You start moving faster and faster. And then you might level out here, you go down some more, and you gain even more kinetic energy. And the whole point of this is, and a good way to describe this is, our kinetic energy gets turned into fun. Whee! Which is the point of skiing. Now this ties back to something that I had mentioned before, circuits. Circuits have a point. They have a purpose. We build them for a reason. Now, sometimes for our classes, that reason may be ham-fisted and simply, hey, we want you to understand how circuits work, but this is the first step so that you can go on and do things like, say, do some small wiring in a project, do some repair work on some of your electronics that may or may not be broken. You're going to need more than what we've done in here, but this gets you your foot in the door. All right. A great example of something that we do is a light bulb. It has a purpose. Its purpose is to light up. Skiing, it has a purpose. You all do it to have fun. At least that's my understanding. It sounds frightening to me. All right. So, in order for us to have fun, in other words, for there to be a change in the universe, energy has to be transferred from one place to another or one type to another. We get fun by going really fast. That means that we end up with a decent amount of kinetic energy, and we got that kinetic energy by being lifted up way up high in the air by the ski lift. The ski lift does work, giving energy to us so we can convert it from one form to another and get something done. Now, what I want you to think about is this. Every time you get something that you want to have done, fun, well, you end up down here. Is that the end? You just go home, you ski once, and that's it? No. What you'll probably do is you'll make your way back over here to the ski lift, where the ski lift will lift you up again so you can repeat the whole thing and we can continually get fun out of it. Same thing happens in a circuit. It's not just one charge that's moving out here. It's all of the charges moving, taking energy with them. And the charges can only move if the circuit is complete. Imagine a long line of people and you've got a line where you're waiting here at the ski lift. Only so many people can get through the ski lift at a time. Now, one of the things that I want to bring up is this. You may be saying that, well, the ski lift always gives a set amount of energy. That's not actually the case. What the ski lift does is if it lifts a kindergartner up here, their mass might be very low. Their mass might be something like, I don't know, maybe 25 kilograms. Whereas a linebacker could also ride the ski lift, and their mass might be something like 110 kilograms. That is a big difference in gravitational potential energy. What the ski lift does is it raises them from a height of 0 to a height of whatever the height of that hill is. And that's the other reason that I like thinking about batteries as a ski lift, because they're not necessarily giving energy as their set amount. How you describe the ski lift is how high up it goes. Now, depending on who gets on there, the ski lift gives a different amount of energy. For a little kid, it's a small amount of energy. For a big person, it's going to be a lot more energy, but we describe the ski lift and how high it is. That's also why with the battery, they have different energies, but we don't rate them in joules. We rate them in their height, 3 volts. All right, so here's the thing. The idea about loop rule works really well with this. You get to the top of the hill and you might have, say, a nice easy slope like this. Or you might have, let's say, coming off of the hill this way, because it turns out that this is just a picture, but in real life, there are many ways down the hill. Let's say that there's a really steep one if you come down this way instead. Okay, and then maybe on the other side, you could have a bunny slope, where it's nice and gradual and you don't get going near as fast, mainly because of frictional effects and air resistance. The important thing is this. No matter which path you take, if you go down the hill this way, let's say that this is a height of 0 and that this up here is a height of 30 meters. You come up here, the battery lifts you up to, the ski lift lifts you up to 30 meters, and you go down this side of the hill, you go down 30 meters, you traipse back over here, and it brings you back up another 30 meters. If you go a different path down the hill, completely ignoring the existence of this one, you could go down this one instead, but you will go from 30 meters up down to 0 and then have to make your way back over. It doesn't matter how quickly you do it or how slowly. If you went down the bunny hill, you'd start at 30 meters and you'd gradually move down until you got to 0 meters, and then you'd traipse back around to get back on the ski lift. That's what's happening in loop rule with all these different paths. So for instance, give me just a moment, I'm going to set that aside. The biggest thing about this is loop rule sets up that no matter which loop you go in, I come onto the ski lift here, go up like this, I go down this slope, and then I come back to the ski lift, I always have to come to the same height. So however much I go up, that's how much I go down. And I might go down maybe, 10 meters right here on the first part of this hill, level out for a little bit, and that means on this second part, I go down 20 meters. Maybe on this one, I go down 25 meters, and then there's a little slope here that slows it down a little bit, and that's 5 meters. Or I've got the whole thing here where it's just a straight 30 meters kind of gradually going down. Doesn't matter. However much I go up, for me to get back to the ski lift and get back on the ski lift, I have to have gone down. So if I go up 30, I have to go down 30 to get back to the ski lift. That's the idea of loop rule. The battery is constantly lifting these charges up. So if I were to draw a circuit, here's a battery, here's a resistor, here's another resistor, and I go like this. Let's say that we've got 3 volts, okay? I go across this, let's go 30 volts. Let's compare it directly to the meters that I just gave you. Let's say it's a 30 volt battery. Charges are lifted up by the battery from 0 volts up to 30 volts. So our delta V is actually a positive 30. Our battery is going to give us heights, give us energy. The charges then move forward at this height of 30, not releasing any energy because they're not going downhill. Then they go across this resistor. The resistor is just like a slope. And so that allows us to convert some of this energy into something else, be it heat for a regular resistor, light for a light bulb, sound for a speaker, all sorts of things. We allow that energy to be released from an electrical form into whatever we'd like it to be. But let's say that this one has a potential difference across it of 10 volts. So it's a little hill that lets us go down 10 meters. So now over here, we went from 30 volts, that's what we've got here, down to 20 volts because our delta V is going to be 10 volts. Now technically, delta would be final, 20, minus initial, 30. This is actually negative 10 volts is what I should be writing there. Negative because the resistor is going to take energy out. It lets things go downhill, releasing energy so that this thing can actually be powered. Now, it's brought us down from 30 to 20 volts. Now, while this is technically a negative, we're always, for the purposes of my class, just going to call it positive, and remember that resistors are going to take energy, whereas batteries are going to be adding energy. These add height, these remove height. Great. So we're at 20 volts this entire distance here, 20 volts, until we get to this resistor. And we go across that, and we end up at some unknown height, but look, right after that, we end up back at the battery here, which we know is at a height of 0, so this means that this must be 0 volts, which means delta V here is technically negative 20 volts. So when I add these up, I go across the battery gives me plus 30 volts. I keep going, go across the first resistor, it is going to take away 10 volts. It has a 10 volt potential difference. And then I go across the other one, it has negative 20 volts. When I add all of these up, 30 minus 10 minus 20 equals 0 volts. Here is Kirchhoff's loop rule. And it's the same thing as going down different paths on a hill while skiing. All right, let's take a look at a different circuit, one that has a couple of different options here. So I've got the battery here, go across, I'm going to put a resistor here, put a resistor here, I'm going to put a resistor here, and a resistor here, and I'm going to put a resistor over here, and over here, and then I've got another resistor here. Now I'm going to fill in a little bit of information for you. Let's see, let's go with the hard route on this. Let's start applying Kirchhoff's loop rule. Okay, let's say that this is a 10 volt battery. It gives us 10 volts, raises us up by a height of 10 volts. Now I'm going to give you the potential difference across this one. This is 3 volts. Okay, so this one raises us up to 10. This one lowers us down by 3, so over here we're technically at 7 is our height. Now I'm going to give a little bit more information. Let's see, I'm going to say that this one is 3 volts here. And then I'm going to fill a few of these things in. Let's say that this is 1 volt right here, and let's say that this is 1.5 volt right here. And that's all I'm able to measure for you. Let's say that I am going through and checking it with my DMM, and right then and there, the batteries run out on my DMM, and I've got a bunch of things that I don't know. All right, so let's apply loop rule and see what we can figure out. All right, so here's what I'm going to do. I'm going to go across the battery. Battery gives us some energy. It's going to raise us up by 10, so I'm going to put plus 10 volts. I'm going to continue going, and I'm going to go across this resistor. It has a potential difference of 3 volts, and resistors take energy, so it lowers us down. We're going to come down here, and we're at a junction here. We're going to talk about that with junction rule, but I've got several different paths I can go. It's kind of like choosing between, do I want to go the bunny slope? Do I want to go the really steep one, dead man's curve? Or just the regular one. I have 3 different options, and you can go whichever one you'd like. So let's go with this one over here because there's only one resistor. I know a bit more about it. I go across this resistor, and I know that it's going to take us down another 3 volts. I come over here, and remember, we're always trying to get from one side of the battery to the other, so I go over here, I cross this unknown resistor, delta V unknown, and I end up back where I started. I have a closed loop. we know that this must add up to 0. So I have 10 minus 3, that's 7 minus 3. So I have 4 volts minus delta V equals 0. That means that delta V of my unknown resistor must be 4 volts. I have now determined that this is 4 volts. It has to be, because then we get back down to our ski lift, so to speak, that will lift us back up and let us go through the whole thing again. Now, there are plenty of other charges. We're not the only ones on the mountain. There are actually billions and billions of other people, as it were, on the mountain, everyone going at their own distinct rate. Okay, let's go a different path here. Let's go with green. I'm going to start here. I like to start on the far side of the battery. We go across the battery, and the battery lifts us up, gives us a height of 10 volts. We go across this resistor. We know that it takes us down 3 volts, and now I'm going to go through the middle one. So I go across this unknown resistor, delta V unknown. I could mark these A, B, C, D, and so forth. We'll do that in the future, but the colors should work fine. Then I keep going. I don't know the potential drop across that. That's okay. That's what I'm trying to find out, it turns out. I go across the next one. It has a drop of 1 volt. And then finally, here's where the upside of the other one came in. I now know that the potential drop across this one is 4 volts. And then I end up back where I started. This is now a closed loop in green, which means when I add up all of the potentials, they must come up to 0. 10 minus 3, great, that's 7, minus 1, that's 6, minus 4. That means that delta V of this unknown resistor must be 2 volts. I'm going to write that in, 2 volts. This is how you do it. And one thing that I want to emphasize, because you've heard me say it a lot, it must be on a closed loop. We're going to find, and in fact, let's go ahead and do this last one here. Where did I put, let's go orange. Start on the far side of the battery. I go across it. It lifts me up by 10, plus 10 volts. I go across this one, minus 3 volts. Then I go across over here, split down this last one. I minus 1.5 volts. Go across an unknown, minus delta V unknown, and then we go over here, we lose another 4 volts to this resistor, and then we end up back where we started. This is now a closed loop. So 10 minus 3, that's 7, minus 4 is 3, minus 1.5. We know that our unknown delta V must be 1.5 volts. 1.5 volts. Now, this is a common problem. We got partway through it. I'm going to mention it again now. Loop rule. All of this only applies in a closed loop. So I've got 10 here. That doesn't mean if I take 3 plus 3, that's 6, plus 4, 10, plus another 3, that's 13, plus another 3, 16. I have 16 volts total that is dropped across these resistors. 10 and 16, that's not what loop rule is about. That is not a thing that you can relate your potential differences, because they're not actually the energy, they're only the height. So that's why it must be a closed loop. You can only apply this when you're drawing one closed loop. Now, here's one of the nice things. I'm going to tack this on here at the end, and then we're going to take a look at junction rule, which should be a lot faster. The thing that's really nice about loop rule, and one thing that I really like about it, is this loop, the red, has nothing to do or no reliance on the green loop or on the orange loop. Now, the circuit is affected by that, but the potentials on that loop must come up to 0. Now, one of the reasons why loop rule is so useful is I could have a million other branches. I could have 1,000. I could have as many as you want, and it doesn't matter what's going on in those. I can still tell a lot about this circuit by applying loop rule. That's one of the things that makes loop rule so powerful. In a really complex circuit that has many different parts all over the place, all of them affect the total circuit, but in any closed loop, we know that the potentials must come up to 0. And that makes it where sometimes you don't have to worry about all the rest of the circuit. You only need to worry about what's happening in one closed loop. Okay, so now we're going to pick back up with Kirchhoffs Junction Rule. Now, this one's actually a lot more straightforward compared to, at least I feel, compared to loop rule. And that's one of the reasons why I think loop rule is a lot more profoundly important, even though they're both equally important, honestly. But loop rule lets you get a lot of information about one closed loop. Junction rule starts letting us combine these pieces of information in other ways. So junction rule basically says that the current entering a junction equals the current exiting that junction. Great. Basically, this one won't take us long to take a look at. What we've got is the following. If I've got a battery here, we'll put a resistor here, and a resistor here, a resistor over here, and a resistor over here. One thing that I like to do that not a lot of people look at it this way is junctions are usually seen as something like this where it splits off, but honestly, a junction can be absolutely any point of your circuit whatsoever, and we're going to talk about that. Let's say that we have 1 amp, or let's go 3 amps coming out of the battery. Now, what junction rule says is you take one spot, one little point in the circuit, and whatever current is coming into it must be equal to the current that is going out of that junction at that point. So right here at this point, I have 3 amps coming in, and what has to be coming out is 3 amps. For my resistor here, I've got 3 amps coming into the resistor, and as we saw with the examples that we saw, it comes in here, goes through this. You could draw a point at any given spot in this resistor, but what you're going to find is there's nowhere else for the stuff to go, so what's going into the resistor is the same that's coming out, 3 amp. Charges are not used up in the circuit. They carry the energy as they move through the circuit. They simply move up in height or down in height, releasing energy that can be used. So we have 3 amps that come through here. Here is where most people consider to be a junction, because we've got a split. But honestly, junction can be applied absolutely anywhere. A junction is just a point anywhere in the circuit. Whatever current is coming into it must be equal to the current that is going out of it. Now, the most interesting places, though, are when you have a branch. So we could say going off this way, we end up with 2 amps going this way. Well, if I have 3 coming in and 2 is going this way, that means that we know going out this way is 1 amp. Because the current coming into the junction, this point, must be equal to the current coming out of that junction. That means that 1 amp is going through here, and it continues going down through here, 1 amp. We saw this in the videos or with the stuff where we developed it. 2 amp is going through this resistor, and that means that we have 2 amp coming in from this side, and 1 amp coming in from this side into a junction right here. So we have 2 coming in and 1 coming in. What's going out? Well, it's got to be 3 amp. And it continues down over here. We have 3 amp going through this, and we end up with 3 amp going into the opposite side of the battery. All right. Hopefully that's pretty straightforward. Usually junctions are only applied when it branches off, but honestly, a junction is just a point. And Kirchhoff's junction rule basically says, at a given point, whatever's coming in must be equal to what's going out. And let's talk about the underlying rule of this. Now, Ohm's law and the power equation and a lot of the other stuff that you all have worked with are things that don't actually apply when you start getting to more and more complex circuits, or they have to be adjusted for more complex circuits. But for the most part, loop rule and junction rule are always true. There are sometimes that we have to update them, that they get a little bit more complex, but these are some of the most fundamental tools when working with circuits, and there's a reason that they have so much more power than, say, Ohm's law or, ironically, the power equation. So I'm going to write this out. Loop rule. The reason loop rule is so applicable is basically, well, you saw, if I go up 30 meters and I have to come back to where I started, I have to go down 30 meters. In short, loop rule is actually based off of conservation of energy. The loop rule applies conservation of energy to circuits. That's actually why loop rule, you're going to find, applies in so many even incredibly advanced places, because what it actually is doing is it's applying conservation of energy, which is a fundamental rule of the universe. This is where conservation of energy comes in our study of circuits. And junction rule also can be applied on quite a few very complex circumstances, places where a lot of the other stuff breaks down. And the reason why is, believe it or not, it relies on a fundamental law of the universe as well. Junction rule applies conservation of charge to circuits. Those charges aren't used up. They're particles. You don't just have electrons popping out of existence or protons suddenly appearing from nowhere. At least in the stuff we're working with anyway. Definitely not in our circuits. They have to move from one place to another. They can't just cease to exist or suddenly pop into existence. And because of that, whatever charges moved into a point must also be equal to the amount that are leaving that point, at least for the circuits that we are looking at. Now, when you get to really advanced stuff with AC circuits and so forth, sometimes you can have a buildup of charge in different parts of points, but it never violates junction rule's underlying principle of conservation of charge. You don't have charges that just appear or disappear. The same thing with loop rule. While it can get more complex, we have never seen an instance that I'm aware of where a circuit has violated conservation of charge or conservation of energy. And as a result, the way we're using junction rule and the way we're using loop rule apply to pretty much every circuit, definitely every circuit we're going to be looking at, and with some slight alterations, they can be applied to any circuit that any member of our species has ever looked at. These are incredibly powerful tools, and we are going to be using them to analyze complex circuits because they rely on fundamental laws of the universe that allow them to be true.